Hi, I'm James Rhodes. Today I'm going to talk about Green Pea recipes as a pre-recorded talk for the LymanRAS workshop. Today's talk is based on work done with a number of collaborators, including the people listed here on the cover slide. In the course of the talk, I'll go through a brief introduction to Green Pea galaxies, then a discussion of the role of neutral hydrogen in Green Pea galaxies, and finally a couple of different recipes for studying high redshift galaxies based on our studies of nearby green peas. This slide is a TLDR for people who need to just pause and look up the references quickly and go on to something else in your life, but I hope you'll stay with me for more of the presentation. And in a similar spirit, I've put here a more comprehensive list of papers from my collaborators in Green Pea research, which I'm putting here because not everybody can be here for the LymanRAS meeting. So, without further ado, Green Pea galaxies are a class of emission line object in the nearby universe. They're named that because of the way they look in images from the Sloan Digital Sky Survey. When you take a false color image from Sloan data, and you use the usual mapping of Sloan filters to RGB channels, galaxies at redshifts up to about 3/10 with strong oxygen-3 emission light up as green sources. Now these are typically fairly compact galaxies, and the spatial resolution of Sloan is about 2 arcseconds, so most of these objects appear round. They're small enough that you're basically looking at the PSF or a somewhat extended version of that, and they're unresolved, so they're green, they're round, and they got described as peas by the citizen scientists of the Galaxy Zoo project. When we look at them in more detail, and in particular look at their spectrum, you can see why they're lighting up in that channel. So this shows one plot with 3 different panels showing key features of green peas for the purpose of this talk. The central panel is the Sloan Digital Sky Survey spectrum, and you can see the very strong oxygen-3 line emission which lights up that green channel. You can see comparably strong H-alpha emission and a whole forest of other lines. We're going to care about this one here, the O34363 line. And we also care greatly about this line. This inset is an HST cost spectrum showing the Lyman alpha emission from a green pea galaxy. And finally here in this inset is a UV image from COS, and we'll hear more about the UV imaging and morphology from Kyun-Ho Kim later in the workshop. Now, I and Sangeeta Malhotra became interested in green peas basically through our work on high redshift Lyman alpha emitters. The green peas show similarities to a couple of things. They show similarities first to the extreme emission line galaxies that you find as foreground objects when you're looking for Lyman alpha in a narrowband search. So the first time I saw a spectrum in my own data that looked most like a green pea was our very first spectra from the LaLa project, and one of the objects that turned out to be a foreground emitter had this booming oxygen-3 line at a redshift of 3/10. The other similarity you see is when you go take a near-infrared spectrum of a high redshift Lyman alpha galaxy, you tend to find this very strong oxygen-3 emission. So this is, in the inset, a spectrum from Emily McClinden's thesis work in 2011. This shows Lyman alpha in red and oxygen-3 in black, and I think this was the first rest optical line emission from redshift 2 and beyond Lyman alpha selected galaxies. And we were able to see in that both the strength of the oxygen-3 line and the existence of the velocity offset, which we had reasonably expected would be there based on earlier Lyman break studies, but had not been observed prior to that. It's now seen as a generic feature and one that we're going to use later in the talk. So, based on these inspirations and on the observation of very strong oxygen-3 from the class of green pea galaxies, we got interested in looking at green peas in the UV to look for their Lyman alpha emission. We weren't the only ones. Elena Henry had an observing program around the time that we were starting to get interested in that, and a couple of other groups also took some of the earliest cost spectra. So these are figures from Huan Yang's paper in 2016, our first published foray into the field in our research group. And you can see a couple of things here. First, these central panels show the Lyman alpha profiles for 9 of the objects in that paper. And you can see the very strong line. You can see also in this particular figure, you see fits to those lines based on Max Gronke's code, and Max was one of the collaborators in that work. And one thing I really love about the green peas is how you can see all this detail, and you see the red peak in the Lyman alpha line, but also the blue peak, which is usually lost to IgM transmission for the high redshift sources. Now, green peas are really useful as analogs of the high redshift Lyman alpha population, and the left-hand panel on this slide shows the equivalent width distribution from Huan Yang's 2016 paper. The heavy green line is for the green pea sample. This is a cumulative distribution of rest frame Lyman alpha equivalent width. Where the cursor is right now is 100 angstroms, and this lowest bin is 20 angstroms, which is about where you start thinking of something as a strong Lyman alpha emitter comparable to the ones that we select with narrowband searches at high redshift. And the comparison samples here are redshift 5.7 Lyman alpha and redshift 2.8 Lyman alpha in purple, which is the closest match, and Galax Lyman alphas at redshift 0.3 from Isaac Wald's work. So the equivalent width distribution is one way in which these are a good analog to high redshift Lyman alpha populations. There's others too. The objects tend to have compact sizes, both the green peas and the high redshift Lyman alpha galaxies. The ionization parameters are similar, and the metallicities are probably similar to the best of our knowledge. So moving on from that, one of the sort of puzzles of these green peas is that they're very active starbursts. That's obvious from the strength of the emission lines. The Lyman alpha tells you need to have a starburst that's not over a few million years in age for at least some of its active population. But on the other hand, well, it takes gas, neutral gas, to power a starburst like that, or rather to provide fuel for the starburst. And on the other hand, neutral gas blocks the escape of Lyman alpha photons from these galaxies, and Lyman continuum as well. So this is a pair of plots, one from Huan Yang's later paper in 2017, and the other from McKinney et al. A couple of years later. Both are plotting Lyman alpha escape fraction on the y-axis and a measure of the gas in the x-axis. For the Yang et al., the measure of gas is the H1 column density, which is measured in this case by fits to the Lyman alpha profiles as shown on the previous slide. And I should note here that this is a logarithmic y-axis. This is an escape fraction of 1 at the top, 10% here in the middle, 1% down here near the bottom. And the other panel, where the y-axis is linear from 0 to 60% escape, is comparing the Lyman alpha escape to a covering fraction of silicon-2 measured from metal absorption lines in the spectra. So both these plots are telling a consistent story. The more gas there is, the harder it is for the Lyman alpha to get out. And that inspired us to go see what we could learn about the gas mass of green pea galaxies, because we do know the gas should be there to form stars, and yet it shouldn't be there in order to let the Lyman alpha out. So we went hunting for these green peas using radio telescopes, and this begins with a pre-selection. This is essentially the selection that Huan Yang and Tianxing Jiang had gotten ready for our collaboration's earlier papers. The key thing here is Sloan spectroscopy and an equivalent width floor of 300 angstroms for the OIII line or 100 angstroms for H-beta. Either one of those being observed securely puts it into the parent sample for the work. Then, in order to see what we could reasonably go after with the radio telescopes, we exploited a correlation between blue luminosity and H1 mass, and essentially end up using the blue flux of the object as a crude predictor of what the H1 flux might be. And then you go look and see what are the radio telescopes that are available, and we went to Green Bank and to Arecibo. For Green Bank, we have coverage of the full northern sky, but a somewhat less sensitive telescope relative to Arecibo. Arecibo had access to basically a stripe of declination from minus 0.4 to 37 degrees. In both cases, we put an upper bound on the redshift, somewhat higher with Arecibo given the larger collecting area, and we had to do some other selections to avoid radio frequency interference with the Arecibo sample. So we went looking with these two big radio dishes, and we came up with 2 dishes of peas. And this is the slightly hacked image from the Green Bank Observatory newsletter, where we had a news story about our results. Moving forward to the science results that were summarized in that article. First off, this is a montage from our published paper of the radio spectra of 8 of these objects. And in the end, I believe we had 19 out of 40 with detections. There's a couple more panels like this in the paper if you go looking for it. But you can see we have detections ranging from extremely strong to adequate. And when you go convert those into H1 mass and correlate them with other properties of the galaxies, there's a couple of interesting things going on here. So, left-hand panel of this plot is showing the H1 mass fraction and comparing it to the stellar mass of the galaxies. And you can see there's a declining trend, so the more stellar mass there is, the less the H1 mass fraction. And we've plotted here the median values for the green peas. Note that half the sample is upper limits, but fortunately that still leaves the median as a well-measured quantity. So we've got median for a couple different bins of stellar mass, and then comparison to the X-gas survey medians. And you can see that this is basically an extension of the same trend as seen in the X-gas comparison sample, which is a star-forming sample, but not as extreme as the green peas. But if you go look at how long the existing gas supply will fuel the starburst, you get an interestingly different story. And basically, the typical depletion time for the atomic gas in the X-gas sample is up near 10 to the 10 years. It's below 10 to the 9 for the green pea sample. So it's an order of magnitude shorter. That's where the live short and prosper title comes from in the Green Bank news story. And you can also look at the distribution of H1 as a function of blue magnitude. And here we have an expectation, a sort of relation from the literature for other star-forming objects. And you can see that a decent fraction of the green peas are up here. This is a +2 sigma line. This is a -2 sigma line for the other population, the comparison sample. And we're seeing a substantial spread with some things that have quite a high H1 mass and others that are quite low compared with that trend line. And the other point here, which sheds some light on the role of the gas in the conditions within the galaxy, is that you can compare the H1 mass with the O3 to O2 ratio. Now, O3 over O2 is most commonly used as an indication of ionization parameter. Anything above 10 is getting pretty extreme. Green peas are getting up into the 30 to 50 range for the most extreme objects. The median is here, though, at a value a bit below 10. And once you get above 10, we pretty much only have upper limits in the Green Pea sample for the H1 mass. So it seems like the most extreme Green Pea galaxies, as measured by OIII, are the ones that are deficient in gas. And that's interesting because from other studies by Jascott and others in the field, we also know that OIII tends to correlate with Lyman continuum escape and with other indicators of generally extreme Green Pea conditions, if you will. So there's other work ongoing in the green peas and radio business. Nissim Kanekar and Shonalika Burkayasta have recently been working on our first paper based on interferometric results. It's too early for me to say anything about that, but stay tuned. With that, I want to turn my attention now to work we've done using green peas as high redshift analogs and deriving from the observations of green peas interesting relations that we hope to apply to the high redshift universe in the foreseeable future. Now, the first one of these is a green pea recipe for metallicity measurement. And the key principle here is that the 4363 line of oxygen 3 is detected in most green peas, and that forms the basis for an extremely powerful metallicity measurement. The reason we don't use the 4363 line for all of our metallicities in astrophysics, or all our gas phase metallicities anyhow, is basically that it's too weak to see in fainter and more distant objects. And what we often fall back on instead is the R23 metallicity indicator, a classic that's based on the ratio of the 3727 and 5007 lines combined to the H beta line. Now, R23 is double valued, which is to say that for many values of the R23 ratio, you could end up with either a high metallicity or a low metallicity solution to the relation between gas phase metal abundance and this indicator. But what we've been able to do with a sample of nearly 1,000 green peas in work that Tianxing Jiang led as part of her thesis with Sangeeta was to calibrate this relation and do it using the OIII ratio as a second parameter. So I'm first going to show you this plane which gives a relation between R23 on the x-axis and 12 plus log O over H, that is the gas phase metallicity on the y-axis. The sun is somewhere up here near the top of the plot. And this panel is for a low, at least low for green peas, ionization parameter, and low ratio of O3 over O2. And we've actually fitted a functional form to the R23 relation as a function of this and this. And what I'm going to do now is play a movie that pages through different values of the OIII ratio. And you'll see this curve move as each panel displays. And the cloud of points is the data points from the green pea sample that fall within that range of OIII ratio. So, as you go through this, you see that the curve shifts and it is doing a reasonable job of falling through the cloud of data points in each bin. We'll go through it one more time. And I'm going to pause here around an OIII ratio of 10 to the 0.7. And from this point on, basically all the data points are either at the maximum of R23 or on this lower branch, the low metallicity branch of the the R23 metallicity relation. And what that means is that as you get to the more extreme emission line galaxies with higher values of OIII, you can basically forget about the high metallicity branch and invert this relation uniquely. So at the end of the day, we get a nice handy plot like this, which we can use to get the metallicity out from the measurement of three very bright, strong lines, the O3 line, the O2 line, and the H beta line, which goes into this R23 measurement. So if you have a galaxy that's a strong emission line galaxy, and you tell me the values of those three lines. We can plop it down where it goes on this plot and read an estimate of its metallicity off the color bar on the right here. And the scatter in that is somewhere around 0.14 dex, so not too bad. If you go to the paper, you'll find more of the details, and the reference to that paper, if I don't have it on this slide, is certainly back on slide 3 or 4 of the set, where I took everything down from ADS. And one last comment is that if you have a sample of 10,000 galaxies and you don't want to look at this plot 10,000 times, there's also a formula in the paper that you can use. And it's a slightly ugly looking formula, but it's only really the quadratic formula for getting the metallicity back out. And you can code it up in Python in a few lines and go to town with your large sample. So that's how we use green peas to give us a recipe for metallicity measurements. The last recipe that I wanted to talk about is dealing with the escape of Lyman alpha from green pea galaxies. Now, this is the classic cartoon by Elie Dweck of Lyman alpha escaping from a galaxy, and we want to know, how does the escape depend on things like H1, metals, dust, velocity offset? And the reason green peas are really handy for calibrating this is that if you go get the spectrum with costs, so you get the Lyman alpha, then you have Lyman alpha and H alpha, you can compare the ratio of those lines to the theoretical value for recombination, and if the Lyman alpha falls short, that indicates that not all of it is escaping. And because green peas are close and bright, we can both measure those escape fractions and compare them with a number of other useful diagnostics. So Huan Yang did that in some detail in 2017. And the next 3 plots I have, next 3 slides, are basically summarizing the results of that work. So on this panel, this slide, we have Lyman alpha escape fraction shown as a function of 4 different kinematic indicators. The first one is the velocity offset of the blue peak of the line from systemic redshift. The second one is the velocity offset of the red peak of the line from the systemic redshift. Third panel is the separation of the 2 lines. And the fourth panel is the width of a line, the red peak, that is. And you can see in all cases, larger velocity offsets and larger line widths tend to go with lower Lyman alpha escape. And all of these are significant, at least at the 99% level in all cases, but the blue peak, they're beyond the 3 sigma significance level. You can also look at how the escape fraction correlates with non-kinematic quantities. So this is the dust abundance, EB minus V, measured in the gas phase using the Balmer decrement. This is the metal abundance, again gas phase. Down here we have mass, and that's one of the weaker correlations going, but still smaller galaxies tend to have more Lyman alpha escape. And the final plot here codes the Lyman alpha escape with the color of the point and plots those points in a space of metallicity against mass. So what you can do is take these different parameters and try to use them to back out a formula for predicting the Lyman alpha escape. And Huan's formula is this one here. It's based on just 2 of the key measurables, EB minus V, which you're measuring from the Balmer decrement, and the red peak velocity. So it's a 3-parameter fit, and when you do that, down here you have the predicted escape fraction of Lyman alpha against the measured escape fraction. It's a reasonably tight correlation. The scatter is just a factor of 2 between the prediction and the measured reality. And what you can do with that is you can take galaxies in the high redshift universe and try to understand whether they are producing as much Lyman alpha as you think they should. And this makes for a potentially very powerful reionization test. So we're taking it to that high Z limit in upcoming Webb observations. What we're going to do is target a protocluster in the cosmos field, which was found by the Lager survey. You'll hear more about Lager from Santosh Harish later in this workshop. And OIII, who has a couple of papers looking at overdensities in Lager fields. This one here is Z7OD1. It's a protocluster that we had a paper discussing that in Nature Astronomy. And Crystal Martin is the PI of a JWST program that's following that structure up using NIRSpec. So what we hope to get is rest optical spectra for several of the bright Lyman alpha galaxies that we already know are there. We already have ground-based spectra with Lyman alpha velocities. And for each one of those, we're going to be able to measure the velocity offset, which is this term. We're going to be able to look for dust extinction from nebular line ratios, which is this term. And we should be able to predict what Lyman alpha should be coming out of them. But on top of that, we can take the H alpha from JWST and the Lyman alpha from our ground-based spectra and measure that ratio and see whether the observed Lyman alpha fluxes are as strong as we would predict using this Young relation up here. And if they're not, it'll serve as evidence of residual neutral gas near those objects. There's a reasonable chance, in my view, that we will find little residual neutral gas there because this is a strong protocluster and should be a strong source of ionization in the early universe, but we shall see. So, to summarize, green peas are really fun galaxies. I've really enjoyed working with them after a substantial part of a career looking at objects that are faint fuzzy dots with spectra that are 5 and 10 sigma peaks with little visible structure for the Lyman alpha and nothing else. It's great to go and see, the Balmer zeta line and all the other fun things that turn up in green peas. But turning to the science you can get out of it, we do find the gas that drives the starburst. Gas depletion times, however, are short, and the most extreme green peas are relatively deficient in neutral gas. And our new green pea recipes allow us to both measure emission line galaxy metallicities on the cheap for the high redshift using R23, and to estimate Lyman alpha escape fractions from Lyman alpha and rest optical emission. And these are nice new green pea recipes. Not every new green pea recipe meets my approval, but these ones you should use for your high redshift galaxies. And I finally wanted to close on a more serious note just by saying that it was an honor and a privilege to use the Arecibo radio telescope for this work, and we're sorry it's gone, and our paper on the atomic mass of green pea galaxies is dedicated to the observatory and to its community. Thanks.